This is the center where we work, in the same place than Carlos, National Center for Biotechnology. And let me just start my talk by showing you the pictures of these two gentlemen who, as early as in year 73, started to play with the concept of genetic engineering, Herbert Boyer and Stanley Cohen. So many of the techniques that we have right now in the laboratories for genetic engineering, cloning genes, and all the rest of it is, to some extent, can be traced to the pioneering work of these two guys. So, and this paper that you see in front of you is considered by some the foundational publication for genetic engineering. Perhaps the title is a little cryptic if you are not in the field, but indeed this was the first time that someone was able to take a piece of DNA from one origin and manage to put it in another place and have it working functionally. So what is this cloning? Well, many of you know what is the basic of it. It has gone through various stages of increasing technical complexity, but at the end of the day, what you have is a DNA, and the DNA can be cleaved with a restriction enzyme, and restriction enzymes make this magic of producing cohesive ends that are compatible with the corresponding cohesive ends of a vector. And then, if you are lucky, you can put that genes into your vector and move it around. So that means that if you get the gene, restrict, digest it, and clone it or ligate it to a vector, then you can put it in a bacterial cells, for instance, or you can put it in another host and have this magic, and to me still very, very interesting phenomenon that one function that is encoded in a gene in a given organism can be transferred and expressed functionally in another place. So this was the starting of the metaphor of genetic engineering, and I will return to the problem of using metaphors in this type of things. And what you have is a system that, well, is there as it is. You can use molecular biology, genetic engineering, and other techniques to tear it down to pieces, and then you can improve or make a model or reconstruct it in some cases, but in other cases, and this is the business of genetic engineering, you can take the pieces that originate in one, say, system and construct something that has new properties. So this is the, say, a golden, dream golden scenario of genetic engineering. You take pieces from one place and make a rational redesign of what you had before to produce something that to some extent is new to nature. So obviously this was a great thing, and very, very early people realized that these technologies and similar technologies could take us to wonderful scenarios. For instance, there's this gentleman called Al Chakrabarty that as early as in year 72 proposed that you can produce in the laboratory bacteria that are artificially trained to degrade petroleum. And well, this is the first case where with a live organism went through a patent procedure. The patent was filed in 72, and it took nearly 10 years to have approved. And even though at the end the bacteria that could degrade petroleum it was not terribly efficient, but at least it was a case where scientists could demonstrate that going to the laboratory you could help to improve properties that were already in nature, and in some cases create completely new ones. By the way, this is a picture of myself with this gentleman many years later. Well, anyway, so let me just put a few landmarks of this, what you may call, or we may call now, traditional genetic engineering. That is, take 1, 2, 3, a few genes at a time and put them in a different host with a degree of rational design. So first of all is this plasmids in vitro, I showed you before. Well, then there's this whole interest to produce hormones, for instance, in bacteria and other vectors. So we have this very, very interesting work in year 85 about production of erythropoietin. And more recently, we had this paper that made headlines by Jay Kisling and his collaborators on production of an antimalarial drug called artemisinic acid. So they still belong to what you may call the paradigm of traditional genetic engineering as it was conceived in the late 70s. So we can use all the techniques and make a jump in time and ask, where are we now? So what we are now is right here. So systems biology, vast amount of data, we can get some connections, in some cases some kinetics in interactions, but the implementation and the use of molecular techniques to biological systems have ended up in this massive complexity. And for an engineer, complexity is the worst possible scenario. So if you want to go and engineer complete biological systems and create properties that are new to nature, we really have to do something about it. We cannot just live with this one at a time engineering of a new biological system. So let me make a semi-philosophical break here and raise the question on how we can describe, deconstruct, and reconstruct biological complexity. So I insist in this philosophical break. I will bring the pictures of these two guys, Habermas and Batimo, postmodern philosophers, that have put some emphasis that I find is interesting in the problem of using metaphors every time we want to address a new reality, and the problem of over-abusing interpretations and metaphors in whatever challenge we have. So, one of the takes of this type of thinking is that all languages for describing reality are metaphoric. So every time we go to a system and try to describe it and describe parts or connections or whatever, we always rely on an analogy to something else that we know. Well, but that's not good. It's not bad because, well, if we have the challenge of understanding and manipulating complex systems, maybe the previous metaphors were not good enough and we have to look for other metaphors. And also, let's keep in mind that all metaphors, all descriptive languages have an agenda. None of them is really neutral. So let's celebrate that this is the case, and let's try to look for new metaphors. And here comes synthetic biology. So synthetic biology, and this is one of the many definitions that are around, is the pursuit of an understanding and design of biological systems to address problems that cannot be solved by traditional genetic engineering or by naturally occurring entities. Obviously, there are many benefits and so on. But what is this all about? Well, you can trace the history of synthetic biology. It has not come out of the blue. It has some precedents in molecular biology, of course, biotechnology, evolutionary genomics. Also, there is this interesting questions on the origin of life, artificial life, orthogonal life, and also, obviously, this massive input of engineering, computing, and modeling. So what is the metaphor that is adopted explicitly in synthetic biology? Well, the metaphor is that biological systems are engineerable systems that are as good or as bad as man-made systems such as a radio. So we have a radio here, we have parts, and obviously the final properties of the radio depend on the components, but also the connections and so. So why cannot we think that perhaps a cell ultimately is something like a machine that makes copies of itself? So by the same token that you have a radio and you can throw it apart in pieces, parts, and so on, and perhaps to construct a different thing, you can think on a cell, in this case a bacterial cell. Sorry, it's not, the focus is not too good. And you just try to go piece by piece and make a catalog of components of that cell. So, and the minimal component of any system is a part. So in biology or in synthetic biology, a part would be the minimum biological object that has a completely defined function. For instance, we have here a repressor and a protein of the DNA and a protein that binds that piece of DNA. So, but, well, that's the minimum thing that you can think of. So you have many parts in biological systems. You can make various functionalities. You have promoters, you have Schendel-Garners, you have terminators, you have reporters, you have, you name it. But, okay, there are many, but still it's a limited number. So we can make a big list of parts that we find in biological systems, not only bacteria, even though many of them are from bacteria because they are simpler than other systems. Well, we can make a big list and just have them as a repository of parts. So by the same token that engineers have parts of transistors, resistances, and so on, we can have a collection of parts with promoters, regulators, and all these type of components. But we can go on, because the parts could be the minimum level that an engineer would use for assembling a complex system. We can take parts and use this abstraction hierarchy and convert them in devices and systems. So what would be a device? A device would be a combination of various parts. For instance, let's suppose that we have two repressors, the lag repressor and the lambda repressor, and if we engineer, and we can do that with DNA, traditional cloning and pasting, we can put expression of one repressor under the control of the other repressor. So what we have here is a defined transfer function between the concentration of one of the repressors and the concentration of the other repressor. You have little of the lag repressor, you have a lot of the other, and vice versa. So this is what in engineering terms would be called a converter, an inverter. So keep in mind that these operations are made by electronics engineers by using transistors, by using resistances, but we can say materialize the same formal operations with the use of biological components that you have there. Well, you can go on now, and you can connect various devices and form a complete system. And by using bits and parts with a defined connectivity and a defined functionality, you can build in complexity in a completely rational manner. So at the end, you may end up something like this. So you have a requirement, like 3 inverters here. Then you can decide how many devices you need, how many parts you need, and then bingo, you just synthesize the DNA, and then you make a system that in principle should have the properties that you expect. One thing very important, of course, is connectivity. I mean, in electric engineering, you can just connect cables, and the only signal that you have moving through the entire system is electrons. In biology, it's more difficult, but in any case, you need to make some connections. And to make that connections, you need standards. And standards is the very basic pillar of engineering. So there is in the history of engineering, there is a before and after the implementation of the thread standards. And this is one of the first. It was just someone that decided that he would propose the community not to use a chaotic a number of screws, but have them always like having a thread with a defined specificity of the angle and the other parameters there. So by the same token, well, standards, we live with standards all the time, so standards allow things that natural, say, scenarios do not allow. And one thing that is important is that allow to uncouple the design from the production, from the assembly, from the deployment. So you can design this in Spain, produce the components in China, assemble them in Singapore, and selling them in Germany. This is something that, for engineers, is piece of cake. In biology, is a little more complicated. Okay, but what is true is that by trial and error, you can use a natural material, say a tree, and you can do interesting things. But you have limitations, and then you adopt standards. And by adopting standards, you can really do things that go much, much further than the natural state of affairs. So what type of standards are applicable in this scenario? Well, the first standard, say, challenge is the language. Biologists have the bad habit of using a completely chaotic language. You name genes with completely arbitrary names. You express units of promoter activity in completely arbitrary, say, measurements of reporters. I mean, it's a complete chaos. So it's important to really use languages that are really defined, and what you, when you read them, you know exactly what you are describing. So you cannot say this promoter is increased dramatically. I mean, what do you mean dramatically? It's 10 times, whatever. So this is something that the engineers went through in the past, and perhaps we can get some inspiration on how to tackle the same problem. So for instance, one of the things that we have made, and many others, is try to reshape a little the language for expression of gene expression events with the Boolean formalisms, in which every event is represented as a 0-1. And you can connect the various, say, elements in each promoter, for instance, in the shape of a logic gate without defined logic here. So we have been through the entire transcription regulation literature, for instance. I have found that regardless of the complexity of any regulatory network, you can represent faithfully the logic and the internal connectivity of the network as a representation with logic gates. Logic gates are the very basic of computing. The thing is that in computer science, logic gates are made with transistors, but bacteria and biological systems do something similar, formally identical, by using other material components. And in that way, you can, for instance, represent biological networks with formalisms that engineers have been using for electric circuits. So this is a system that we have studied for a long time, and for the degradation of silane in a bacterium, in a soil bacterium called Pseudomonas putida. And we see that these representations with arrows and hammers that biologists like so much can be really reconverted into a logic circuit where you have defined inputs and outputs, and you can really know a lot on how the system works just by having this type of formalism applied. There's this other issue on standardization, and it's about what engineers call metrology, how to measure things. I mean, what are the basic functions that biological systems have, and how can we measure them? Well, there are two basic, very, very basic events in biology. One of these is transcription, other is translation. Okay, so this proposition, and it's still a proposition, is not widely accepted, that perhaps polymerase per second can be equal to some extent to electric current. So perhaps the way to make these connections between different bits and parts in a biological system is by assigning a number to polymerase per second, that could be the intensity of transcription. And this is something that perhaps we can measure in various ways. But the same thing with translation. So you have POPs, polymerase per second, and RIPs, ribosome per second. Obviously, these are still very primitive attempts to standardize measurements, but I think they are steps in the good direction. The other thing, obviously, is standardization of DNA synthesis. And as was mentioned before, modern technologies allow addressing the problem of sequencing, but also allow, as you know, more and more to synthesize bigger and bigger and bigger pieces of DNA. And the synthesis of DNA is becoming more and more similar to programming, say, a biological computer, operation. So, well, you name it, maybe certainly in my laboratory and many other laboratories, just this DNA synthesis for complex constructions is now becoming very, very similar, very popular. So what you have at the end is that once you have figured out the properties of the system that you want, you go to your computer, you type your sequence, you make sure that you generate the right collection of parts, connectivities, and all the rest of it, and you go to a company, or if you are lucky, you do it yourself, and you synthesize that piece of DNA. And then you clone it in your favorite vector, and you try it. It may work in some cases, in other cases it doesn't work. I will return to that, but obviously these cutting and pasting DNA procedures that many of us are used to do for many years probably will come soon to an end because of the cheap DNA synthesis that are being more and more popular. Okay, well, this is nice. You see cells as machines. You have this standardization, but what can do with all this? Okay, I'll show you just a few examples, some of them from, one of them at least from my own laboratory. So for instance, we heard before about this pattern formation. So pattern formation was told before is something that is connected to development. So, well, one synthetic biologist can say, well, why don't we try to reproduce in a completely engineering approach something that is a pattern development? So someone called, what was his name? Ron Weiss in Princeton by that time, so was able to play with some parts and devices that he could recruit from a phenomenon in bacteria called quorum sensing, and at the end he was able to make bacteria to develop patterns. Well, these pictures made it to the front line, to the first page of the New York Times, so you may have seen it before, but indeed it was the first time when a synthetic approach was able to reproduce to some extent something that biological systems made spontaneously with a lot more of complexity. There's this other funny story about making E. coli cells able to respond to light, and it was the work of Chris Voigt in Berkeley by that time. So he was able to make a fusion between a transcriptional regulator and a photoreceptor, and then he engineered that in E. coli, again by using these parts, devices, modules, concept, and then what he made was to do a kind of super big Petri dish that was illuminated with his own image. And then what he got at the end was a Petri dish that was seeded with a layer of bacteria that reproduced his picture. So, well, I mean, you say, well, you know, so what, but it has to say that this is remarkable because this is one of the cases where you can see that you can engineer bacteria to do something new to nature. This has never happened in nature before, excepting when this gentleman did it. Well, only games? Well, in fact, we are getting into something serious because you are aware that we are moving from a petroleum-based economy and a petroleum-based society into something different because obviously petroleum is running out. I'm sorry that you cannot read the small letters, but what it tells us is that our entire lifestyle, all the materials that we use, the painting, everything depends on about 20 chemical molecules that these building blocks can be converted into secondary chemicals, intermediates, and then being converted into a large variety of products for industrial applications, for transportation, textiles, and you name it. So most of these building blocks, until now, have relied tremendously on oil. But as I said before, oil is running out, and there's this idea that we have to rely more and more and more in biological waste to produce the same intermediates eventually, and then at the end to get the same products if we want to maintain basically our type of society that we have here. So in that respect, in the last few years, there is this incredible attention to synthetic biology as one of the enabling approaches, perhaps to move from this oil-based economy into other type of society. So the World Economic Forum has published just a few weeks ago this report describing the top 10 emerging technologies for 2012. And then look at this. The first is informatics for adding value to information. I mean, we all know that we live in a information overflow. But then the second is synthetic biology and metabolic engineering. So you may say, well, but we had this long time ago. Why you want to have, why you put this in as a second technology? Well, we have something of the previous situation, but now this adoption of real engineering, not any longer a metaphor, but real engineering into biological systems is expected to really push the field much, much further than we are right now. And I'll show you just a couple of examples. Well, you may say, well, how can we see the value of these synthetic products or these biological new to nature, components? Well, things as simple as having an enzyme that can be engineered with biotechnological procedures with some addition of synthetic biology for producing a detergent that is able to dissolve, fat under low temperature. Well, some people have made calculations of how much energy goes to laundry in a big city, for instance, and well, you can make an estimation of the savings in energy that you can do by having something as simple as a bacterium that is engineered to produce large amounts of this enzyme that is able to make the job at lower temperatures. Well, if you are interested, you can go to this webpage, for instance, and you can make some calculations on what would be the benefits in quantitative terms of having a detergent that works at low temperature versus having to use all the energy to heat up the corresponding laundry. So, and the calculations are really, really interesting in the sense that they can tell you that these approaches really help to not just to address health problems or fight cancer or what we discussed before, but also it makes biology to become an enabling resource for industrial technologies and also for the society as a whole. There's another example that where you see the benefits of using these approaches for other purposes. This is a project that we made in a laboratory, and well, anti-personnel mines, the problem that is out there. It would be ideal to have a sensor that would detect vapors of explosives on the surface. So what we made, some of my collaborators, was to develop a bacterial biosensor able to detect 2,4-DNT. I'm sorry I have to rush to tell you these things. I will be happy to give you more details if you are interested. So what we made was to take this approach of logic gates, circuits, parts, modules, and we implemented this little circuit here that was able to capitalize the natural properties of a protein called Sylar to detect not only M-silane, but also to detect the nitrotoluene. And we engineered that in the shape of a logic gate. Well, these are, say, lab experiments. You take a Petri dish, and then, well, you can see with a color code that you just spray bacteria on a Petri dish, and in the middle of it, you have, to 4-DNT, you have a strong signal versus other controls that don't produce this signal. And you can go even to the field and make these experiments, and you spray, again, this sensitive bacterium, and you can really see this type of phenomena by which the sensing bacteria is able to spot underground presence of 2,4-DNT. I mean, this is what is called a biosensor. We have many examples of that. Other people have developed similar concepts for many other compounds. But it's the idea that by standardization, you can really implement and develop properties in bacteria and other, in the future, organisms with very, very interesting properties for a large number of applications. So I leave you with this slide. You may or may not like it. I'm convinced that this is true. We can do better than nature. However, we still have a real problem. And the problem is that we need a real more science here, because we can synthesize a lot of DNA, let alone sequence a lot of DNA, but we cannot really handle more than about 20 genes at the same time. So the moment that you put more than 20 pieces, things start to become very unpredictable. So you will need to fill this 400-fold gap between the technical capability to engineer a biological system and the knowledge that we have to do something that is reasonably predictable. So I'll leave you with that slide, and perhaps with the previous one. And this is the end of my talk, and thank you very much for your attention.